Hi, I'm Rudy Sandbergen, and the topic of this week's lectures is sustainable sources of heat. A massive source of heat is of course the sun, so let's start with this. After this lecture, you should be able to make a rough sketch of the solar spectrum and indicate the types of radiation it contains. You should be able to explain quantities like irradiance and irradiation. And finally, you should know the typical values of irradiance and annual irradiation at Earth's surface. Note that the various technologies for harvesting solar energy, such as solar thermal collectors, will not be discussed here, but in the next lecture. You probably heard of X-rays, microwaves, and radio waves. Although they seem very different, they are part of the same phenomenon, electromagnetic waves. They only differ in wavelength. Electromagnetic waves with the shortest wavelength are called gamma rays, shown on the left. Waves with the largest wavelength are called radio waves, shown on the right. The human eye is sensitive only to a narrow spectral range. The visible spectrum that ranges from violet with a wavelength of about 400 nanometer to red with a wavelength of about 700 nanometer. Light with a wavelength less than violet is called ultraviolet, UV, and light with a wavelength larger than red is called infrared, IR. All objects, even as you are watching this video, emit electromagnetic waves. Objects at room temperature emit infrared light, not visible to the human eye, but it can be picked up by a thermal imaging camera. If we heat an object beyond room temperature, we can feel radiation coming off. Think about the radiator in your house. If we keep heating an object to several hundred degrees Celsius, we start to see a visible red glow. If we continue to heat it to a few thousand degrees, we start to see a bright white glow. This means that increasing the temperature, the emission does not just become brighter, it also shifts to shorter wavelengths, from infrared to the visible part and eventually the UV part of the spectrum. To describe this behavior, I'm going to use spectral irradiance curves. These are the graphs of spectral irradiance versus wavelength. Such a graph shows how the power emitted by a light source is distributed over the different wavelengths. By integrating this curve over all wavelengths, that is, taking the area under the curve, we obtain the irradiance in watt per square meter. This is the power density indicating the total radiant power in watt emitted per square meter of surface area. The black-body radiation law describes this behavior. This graph shows that indeed, cold objects emit only infrared radiation with long wavelengths of several microns. With increasing temperature, this radiation becomes brighter and shifts to shorter wavelengths, into the visible part of the spectrum. The sun, which has a surface temperature of more than 5,500 degrees Celsius, has its radiation peak in the visible part of the spectrum. It also emits UV and infrared light. The area under the curve gives the power density in watt per square meter of the emitted light. From this, we get that every square meter of the surface of the sun emits 64 megawatts. We now know, based on its temperature, that the sun's surface emits 64 megawatt per square meter. But what is the power density incident on Earth? To calculate that, we need to know the distance from the Earth to the sun, which is 150 million kilometers. We also need the radius of the sun, which is 0.7 million kilometers. Note that Earth, with a radius of 6.4 thousand kilometers, is tiny by comparison. Here the dimensions are drawn to scale. If the blue arrow represents the distance between Earth and Sun, then the Sun is only a small red dot. On this scale, Earth is tinier than a single pixel on the screen, so invisibly small. The Sun radiates its energy in all directions. Therefore, the solar energy will be more spread out by the time it reaches Earth. This is indicated by these concentric spheres. The area of the sphere is proportional to r squared, so by doubling the distance, the energy is reduced by a factor 4. When we plug in the numbers, we find that at Earth, the incoming irradiance is 1360 watt per square meter. This is called the solar constant, an important number to remember as it gives you the maximum power density that can be obtained with solar power on Earth. We must keep in mind that Earth's atmosphere also reflects and absorbs part of the irradiance before it reaches the surface. This graph shows the spectral distribution of sunlight above the atmosphere in yellow and at Earth's surface in red. The extraterrestrial spectrum closely resembles the blackbody spectrum that we saw before. However, the spectrum measured at Earth's surface is less smooth. Water and carbon dioxide molecules absorb specific parts of the infrared light, while ozone absorbs most of the UV light. Under a clear sky, the maximum incident irradiance is about 1000 watt per square meter. Of course, when it's cloudy, the irradiance is much lower, depending on the thickness of the cloud coverage. Note that the spectrum I just showed is the global irradiance, which is the sum of three components. Firstly, direct sunlight coming directly from the sun, and secondly, diffuse sunlight coming from the blue sky or clouds. If we consider a tilted surface, we also need to include diffuse light reflected from the ground. There is one final aspect that we must account for, and this is the sun's zenith angle. If you point one finger straight up and another finger towards the sun, then the angle between these two directions is called the sun's zenith angle. When the sun is directly overhead, this angle is 0, and when the sun is on the horizon, during sunrise or sunset, this angle is 90 degrees. The average zenith angle is lower near the equator and larger near the poles. This affects the amount of irradiance received in two important ways. The first effect is a geometrical effect. Consider a beam of sunlight with a cross-section of 1 square meter, incident under a zenith angle theta. The larger the zenith angle, the more the irradiance is smeared out. It can be shown that irradiance received by a horizontal surface is proportional to the cosine of the zenith angle theta. This explains why it is colder near the poles, where the amount of irradiance received per square meter is much less compared to the equator. A second effect is that when the zenith angle is large, the incoming sunlight has to travel a longer distance through the atmosphere, and more light is absorbed before reaching Earth's surface. This factor, 1 over cosine theta, is called the air mass. The spectrum that I showed before is the standard air mass or AM1.5 spectrum. Other spectra, like AM1, AM2, etc., are also available. The extraterrestrial spectrum, shown in yellow, is called AM0, as it is not filtered by Earth's atmosphere. Thus far, we have discussed irradiance, the instantaneous power density in watt per square meter. A related quantity is irradiation. This is the total amount of energy in kilowatt hour that a surface receives in a day, month, or year. If we consider a sunny location near the equator, how much would the total irradiation be for 1 year? If we assume 1000 watt per square meter is received constantly, day and night, this corresponds to 8760 kilowatt hour per square meter. However, we have to correct for the fact that Earth rotates, and therefore the irradiance averaged over day and night is a factor of 4 lower. This gives an annual irradiation of nearly 2200 kilowatt hour per square meter for a sunny location near the equator. If we then look at the annual irradiation measured at Earth's surface, we see that it's indeed around 2200 kilowatt hour near the equator, with values up to 2500 kilowatt hour per square meter for the Sahara Desert. If we then look at locations further away from the equator, and perhaps also cloudier, such as Northern Europe, the annual irradiance there is only 1000 kilowatt hour per square meter. We saw that closer to the equator, the annual irradiance is generally higher. There is another advantage of being close to the equator, and that is that there is less seasonal variation. The left figure shows the monthly irradiation for Egypt. This shows that the monthly irradiation in December is only about 30% less compared to the maximum irradiation in June. This is very different for a country like Netherlands, shown on the right, where the monthly irradiation in December is 80% lower than in June. This demonstrates the importance of taking the seasonal variations into account, especially for locations further away from the equator. This brings me to the end of this lecture. From the fact that the sun is glowing at 5500 degrees Celsius, we can understand that the sun irradiates the Earth with UV, visible and infrared light with an irradiance of 1316 watt per square meter. The annual irradiation on the surface of the Earth varies roughly between 1000 and 2500 kilowatt hour per square meter, depending on latitude and cloud coverage. In the next lecture, we will discuss the technologies used for harvesting this energy.